Okay, we are getting close to finally justifying the name machine learning in the title of this course as a result of a path through statistical physics. Like I said at the beginning of this course, this was not a course for plug-and-play machine learning, like, I don't know, using AlphaFold, but rather a course in which you first understand the physics and then address the question, can machine learning help us in doing this more efficiently, more accurately, or improving to some extent, according to some definition, the performance. Now, we'll see how far we go today, but machine learning methods are good at one thing in particular, is seeing connections that human eyes doesn't see, and exploiting these connections to improve policies or choices, or to generate configurations according to existing distributions. Now, we see that this is particularly relevant in a number of fields, topics related to this course. But let's first go back to the topic we were tackling during last lecture, that is, how do we interpret molecular dynamics equations in a very large dimensional space, right? What we did last time was to assume a dimensional projection based on the notion of collective variable. So collective variable is functions of the configurations typically. So a CV is a function of X appointing configuration space. And this function must have several important properties. It should be sufficiently descriptive to distinguish between the states I'm interested in studying. Say, I'm interested in studying proton folding, the collective variable should be different from the unfolded to the native state, otherwise I'm learning nothing from it. But this is not the only important property that a collective variable should have. It should also be a slow variable, so that the dynamics can be considered adiabatic in the CD subspace. And by adiabatic, I mean exactly what adiabatic means when you draw adiabatic diagrams your first year in thermodynamics, in your freshman thermodynamics, where you draw on the PV plane, you draw a continuous line, for instance, and these continuous lines imply that each point is basically at equilibrium. Of course, it is not truly equilibrium. This is a delicate point that people don't touch during freshman courses because probably it's a little bit too advanced. Each point is at equilibrium, but you do transform from here to here. So the system is at equilibrium, but it's not entirely stationary. There are transformations of the system. But equilibrium, by definition, means that nothing changes. So what really this continuous line means is that as you go from this point to the nearby point here, you do it sufficiently slowly to allow the system to equilibrate around it. So this is the adiabatic limit that we have already discussed many, many times. Now, the collective variables that we describe here should in principle be defined in such a way to obey or fulfill these adiabatic conditions, meaning that all the orthogonal, whatever orthogonal means in a differential geometric sense in such a complication setting, but all the other variables are very fast, or better, have much faster equilibration times, so that the slow equilibration process, the one that involves really visiting configuration space and possibly covering ergodically large portion of configuration space, are associated with significant changes in the collective variables that occur over a very long time. That's fantastic, because if you can figure out your collective variables, your problem ceases to be 500,000 dimensional and becomes m-dimensional. M is the number of slow collective variables. However, there are many problems that remain open. First, how many collective variables there are? How many slow variables there are? Well, if you think about it, the number of collective variables somehow is related to the dimensionality of the intrinsic manifold. Remember, the intrinsic manifold is a subspace where the configurations concentrate at final statistics, right? Now, clearly, this is not an identity. The number of collective variables is not necessarily equal to the dimensionality of the intrinsic manifold. Why? Because there could be direction in the intrinsic manifold that are slower than others. However, it is certainly lower or equal to the number of dimensions in the intrinsic manifold, right? So one question is, what is the dimensionality of the intrinsic manifold then, right? And I'm not sure I have the time to go through the very recent machine learning algorithms that have been developed to this end. There is one that I was planning to cover by Lio and coworkers, who basically exploits one fundamental idea. Suppose you have Brownian, so I will just basically sketch the idea. This is not anything that I will ask in the exam, just to give you an idea how you can sort of combine ideas that we developed in this tool, in this course, to come up with algorithms that learn geometric properties of systems. Okay, so first of all, we described the fact that for sufficiently slow time resolution, the dynamics can be described by Langevin dynamics. Right? Well, this is the linear noise. And we also emphasize that for very short delta t, the noise dominates over the force, because the contribution to the noise scales like the root of delta t, while the contribution of the force scales like delta t. So for small delta t, you're dominated by noise. This means that any stochastic trajectory is locally a Brownian trajectory, and then you might see a drift in one direction if you look at it for a very, very long time. Now, intrinsic manifold means that this trajectory does not perform Brownian motion in the 3n dimensional space, but it performs a Brownian motion in the n-dimensional space, the dimensionality of the local dimensionality of the intrinsic manifold, right? If you want to visualize this, think about alanine dipeptide. Now, I don't remember exactly how many atoms are in alanine, but let's say there are in total 20 atoms, which is a fair order of magnitude for alanine dipeptide. So this should be 20 times 3. We're talking about 6-dimensional space, right? But alanine dipeptide is basically most of the motion is basically frozen because of the covalent bonds, and because some of the angles are basically stuck. As a matter of fact, there are only 2 degrees of freedom that alanine dipeptide can actually exploit. There are the 2 dihedral angle phi and psi. So even though the dimensionality is 20 times 3, 60, most of these dimensions are constraints, and the result is on 2-dimensional. Now, actually, it could be slightly more, or slightly less, because some of these dimensions, even on the dihedral angle, may be more constrained, but you get an idea. So, a very smart way to estimate the intrinsic manifold is to analyze this Brownian motion and ask yourself the following question. Is this Brownian motion consistent the Brownian motion in a space with m dimension. What is the dimension m that better describes this Brownian motion? How do you do that? Well, Brownian motion is very, very simple. You can compute everything you want in Brownian motion. You can compute the mean square displacement, you can compute, so you can compute how many points you expect to find in the neighborhood of a point in m-dimensional space. Okay? So what people do, they look at spheres around each point in m-dimensional space, and they count the number of points in, say, layers of the spheres. Right? Why layers and not just a sphere? Because by computing different layers, you can remove the radius of the sphere as a parameter and get just a pure number that tells you more or less dimensional number that relates exactly how. So stated differently, the number of points, the volume of a sphere, of a layer of a sphere, depends very, very strongly on the dimension of the problem. Like, this is a famous example when you want to fool yourself with the curse of dimensionality. If you ask yourself, how much of a volume of a sphere in d dimension lies in the layer of radius dr, you discover that in the limit of large dimension, basically all of the volume of the sphere lies in the last layer, not in the bulk. It is counterintuitive because our brain is trained to think in terms of 3 dimensions, but in, say, large dimensions. So the number of points that lay on the layer of the sphere is a very sensitive probe of the dimensionality of the system, right? And people they count how many there are, and then they compare the number of points that they find in the bulk and in the layer to the expected estimates you would have for d dimensions. Okay? And this provides a completely data-driven estimate of the intrinsic dimension. Okay? And it's a form of machine learning. I want to emphasize this. I think machine learning is not in any way synonymous of neural networks. I define machine learning in this course as a data-driven procedure that doesn't resort on any model for the forces but purely on data to learn about properties that are intrinsic to your molecular system. In this case, the dimensionality of the intrinsic manifold. And something quite interesting happens. First, proteins have typically, say, 200 amino acids, right? Human globular proteins, 200-300, median is 300. Of course, then you have large proteins, membrane proteins, and you have chaperone-assisted protein. You get all sorts of things. But let's say if I look at globular proteins in the human proteome, I think 200 to 300 is a fair estimate of how many amino acids there are in the protein. Okay? Each amino acid has on average about 20 atoms, right? So you immediately count that the number of dimensions of the protein is gigantic. But the intrinsic dimensionality is always between 10 to 15, typically. Okay? So the intrinsic dimensionality is widely smaller than the configuration space dimensionality. So this is a good news, but hey, 10 dimension is much smaller than 500,000, but it's a huge number. Let me give an example. You may ask, suppose you want to solve the following problem. You want to fill a box with spheres that don't overlap. This sounds like a mathematically abstract problem for proteins or biophysics, but say I want to consider a configuration space and I want to put configurations that are sufficiently far apart to be distinguished, right? And sufficiently many so that I can cover all the relevant part of configuration space. It sounds like a Say, okay, with the resolution given by this radius, I don't need to know all of this configuration. I put one every given radius, right? This could be a meaningful thing to do if you wanted to subsample configuration space. Now, when you place spheres in a box, some void, even if you put them in close packing configurations, some void remains because of the geometry of the sphere, right? But normally, when you try to pack your, say, when you try to, when you play pool, and you have this triangle where you fit the boxes, the spheres, the void is relatively small, right? You don't worry too much. Now, in 10 dimension, the fraction of the volume in 10 dimension of a box that is filled by non-overlapping spheres, so this volume is 0.003% of the volume. You are dominated by void. So the curse of dimensionality hits hard, even at 10 dimension. That's the message that I want to give you. Yes?
I didn't understand why this is a problem. Like the spheres that we are, is it related to the spherical shells that?
No. First of all, let me emphasize, this is just an example to show that 10 dimension is much less than 500,000, but a space with dimension 10 is already well in the regime of a large dimensional space. And by regime of large dimensional space is a regime where things that we think don't matter in 3 dimensions become dominant. Okay, so as an example, I consider the problem of taking a box in D dimension and filling it with non-overlapping sphere in maximum packing configurations. And I try to motivate that this is not entirely unrelated to the molecular problem, because I might decide that instead of generating zillions of configurations, I generate configurations that only are they can get as much as the minimum distance is twice the radius of the sphere. So that by doing this, I could cover the entire configuration space. First of all, the number of spheres you would need to put in a 10-dimensional sphere scales very badly, exponentially with the number of boxes. So already, this configuration would be a lot. But then you would have a second problem, that if you only count what happens within the sphere, in D dimension, where D is large, the fraction of volume that is not inside any of the sphere is not a minority fraction of the total fraction. As a matter of fact, is the vast, overwhelming majority of space. This is counterintuitive because in 2, 3 dimensions this doesn't happen. Actually, in 1 dimension, it's 0 because spheres are segments, right? And in 10 dimension, the fraction of space not filled by spheres is a fraction of a per mil. So you're dominated by void. Therefore, 10 dimension is well into the regime of the large dimensional spaces. Okay, so this has implication because it is unlikely that we will be able to do anything meaningful and statistically relevant if you want to be greedy, meaning exhaustive, in molecular simulations. Because even if we reduce things to 10 dimensions, sampling a 10-dimensional space is a horribly complicated problem. Sorry, covering uniformly, like with a lattice, you need to do important sampling. You need to put your configurations only where they matter, right? Otherwise, you're lost. The only reason why molecular simulation, this is a very, 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 very important point of this course. What I just told you is that what works in other fields will not work with molecular simulations. For instance, if you want to study fluid dynamics, people do lattice Boltzmann, which is placing field values on Navier-Stokes in this case, sorry, mixed two. Or you want to study complex fluids, you do lattice Boltzmann. What do? You put the lattice and you define densities in each point of the lattice. This works great for 3 dimensions. But it's a greedy approach because every single corner of space is equally filled by a variable, right? Also, people doing lattice field theory in particle physics do the same. They have four-dimensional space, 3-dimensional plus time, and they do that in a greedy approach. Now, if you try to do it in molecular simulation, you're lost because you cannot go below 10 dimensions. So, the only reason molecular simulations work is because we do important sampling, meaning that even if we might use molecular dynamics, we might use Monte Carlo, we might use them to build Markov state models, but these dynamical variables that we generate are not uniformly distributed in configuration space. They are focused where it matters. Okay? But now, the hope is that we can find a sufficiently small number of collective variables. They can be up to 10, 15, hopefully they are less, right? So we want to understand, A, how many collective variables do we really need? And how can we find them in a data-driven way? Because what we discussed last time is physical-chemical intuition can help us. It can go a long way, but it can also fool us. We discussed that if we don't capture all the relevant dimensions, we might be fooled by the fact that the same state might indeed contain two states within it. There are ways around it. Maybe you can do clustering, structural clustering within a state and try to see whether configurations like to cluster in different directions. Like the example was, remember last time we have this example in which there was a sort of a C-shaped energy landscape with maybe some states here, here, and here, and if you use only this collective variable, you don't distinguish between these two states, which are very, very different states. However, you need to do additional steps. You take the configurations within this value of the collective variable, and you do dimensional, if you could do, for instance, structural clustering with the k-means algorithm, for instance. And this would immediately generate two clusters. So people have used these methods for, if you read papers, you find this combination of methods. People use intuition to get an idea where things go, like they choose to be guided by their chemical, physical intuition to dimensionally project on a moderate number of dimensions, 2, 3. Maybe they consider a couple of pairs of these planes, because we like planes, because we can understand things. And then they use additional data-driven algorithm to dissect the information, for instance, structural clustering within the same state, okay? So this is, I would say, this is the way to go until 10, 15 years ago. Until 10 to 15 years ago, people have relied on these methods to extract information from molecular simulations, okay? Structural information, and then of course measuring how often you go between clusters, you get also some kinetics, okay? But things have changed, and I keep on changing. And now in the era of machine learning, we are forced and urged to ask the question, can we do this more systematically? Okay? And much work has been done in this direction, of course. And today I will briefly discuss concepts that come from the interplay of mathematics community and chemical physical communities. So on the mathematics side, I would like to call Koifer and Latham are two mathematicians that devised the formalism that I'm going to present to you, that is the diffusion map formulas. Okay, but I will come to that. But these concepts have been imported into molecular simulation by a number of people, but mostly I would say by Frank Noé and Cecilia Clementi and co-workers. I probably don't make justice to other brilliant scientists that have equally or almost equally contributed, but I think that their contribution has been prominent, I would say, in doing whatever I'm going to tell you now. Okay, so basically taking ideas from mathematics, and if you try to read these papers hard, it's really hard even for a theoretical physicist, because they're really in the language of mathematics and data science, and translate them into the field of molecular simulation. Now, in the notes that I've distributed, and in the videos for statistical theory course you find online on my channel, if I remember well, I provide a much more thorough mathematical introduction. Certainly on the notes, you find a much more thorough mathematical introduction. But this, in this lecture and in the exam, I'll give also the composition of the students in this course. I decided not to go so much into details of mathematics as I would have done for, say, a course of theoretical physicists, and remain slightly on a more higher level of description, okay? Just to give you the flavor of what these tools do and why they are relevant. But nowadays, in the era of machine learning-based code and scripts, getting a script that implements the underlying mathematics is basically straightforward, okay? So what is the idea? Well, I would say, let me start with a problem that most intuitively generated collective variables have. And that's the problem that we would like to solve with data-driven collective variable definition. The problem with heuristic definitions of collective variables is that they mostly rely on structural proximity. Now, I let you write, and then I comment what I mean by this sentence. Well, going back to the example that I was quoting before, you see exactly what I mean. I had my C-shaped energy landscape with some at a stable state here, here, and here, right? And then this was my collective variable, x, which is of course suboptimal because first of all, it does not, certainly the motion along the x is a small motion, but it hides important structure. So what did I tell you? Okay, if you see that there's a state here, because if free energy will have a deep in this region of the collective variable, you additionally perform structural clustering. You see there are configurations close to each other here, then a gap, and then configurations that are close to each other here. And you use this structural clustering to infer the existence of two metastable states here and here, right? Makes a lot of sense. Because the underlying assumption that we are making is that structural proximity is a very good proxy of kinetic proximity. What do I mean by kinetic proximity? I will give a proper definition in a moment, but intuitively, two states are kinetically close if they can easily diffuse onto each other. Say you have two slightly different configurations of a protein in the native state. Maybe one of the side chains aromatic ring is slightly displaced, but it takes just a few fluctuations to go back and forth, right? These two structurally close configuration, this is the protein and this is the aromatic ring, are structurally close because if you compute the mean square radius displacement is small compared to that of, say, widely different configurations. But they are also kinetically close because all it takes is a little bit of random motion of the dihedral angle to go from one to another, right? So the idea is that if two configurations are close, then they should belong to the same state, right? True, most of the times. Not always. And when we deal with high-dimensional system, anytime something is most of the time, you know, some kind of an emergency bell should start ringing. For instance, remember, most of the volume is in the spheres in two dimension, but most of the volume is outside the spheres in d dimensions. So whenever something is closed most of the time, but we are dealing with large dimensional system, I think the argument we have from physical intuition should not be trusted too much. Okay, so let me give an example of how things can go wrong. Suppose the metastable states have very different entropy, which, by the way, happens a lot of time. For instance, the entropy of the unfolded state of a protein is very different from the entropy of the native state of a protein, right? So in one dimension, I can easily draw two states with very different entropy. It's a double well. Like this. Now these are clearly, see, if this is the temperature, these are clearly two states, right? And the energy at the bottom is close. I wanted to make it equal, and it turned out to be slightly higher for this, but it doesn't really matter compared. However, the free energy of these states is very different, because if you count how many times a molecular dynamic simulation spends in this, it will be much longer than the time it spends on this. Why? Because here there's so many states you can keep on populating, right? So in other words, the free energy, Helmholtz free energy F is U minus Ts, which means that this has much more entropy than this, right? And if you think about it without going into the formulas, but it's clear that the entropy comes from the partition function. And if there are many states with comparable energy in the partition function, you differentiate the logarithm of the partition function with respect to temperature, you get the entropy. And therefore, the partition function of this state is clearly much longer than this, because here there are few states with energy low. Here there are many states with energy low, right? Do you see this? Very good. But just because this state has so much more entropy than this state, then things can be fully new a lot. Look at these two configurations at the border of this broad state. They're structurally very different, right? Look at these two configurations. They are much closer structurally. But if I associate these two configurations together because they are closer than this, I'm fooling myself because the dynamics, which this geometric criterion completely ignores, okay? The dynamics knows that if I start the simulation from here, it will fall into this basin. And if I start the simulation from here, it will fall into this space. So some dynamics information is required to properly associate configurations to states. And in fact, Frank and Cecilia, who developed some of these tools and translated, imported these tools from mathematics, were mostly interested in constructing Markov state models. And to construct Markov state model, you need to find the Markov states. And therefore, the problem of finding robust criteria to identify states. Okay? You with me? Okay, so if structural proximity by itself is not a good measure, or may not be a perfect measure, you know, there's always degrees of how bad you can screw up. You can be more or less okay, or be badly wrong, but certainly you're not ideal. Now, if structural proximity is not the best definition you can get, what can improve it? What is a better definition? And so I want to discuss with you today the concept of kinetic distance. Well, the kinetic distance between two configurations, x and y, is a distance, which means that, first of all, d of x must be 0, it must be positive definite, and dxy must be equal to dyx, and it must obey the triangular inequality. Now, let alone the triangular inequality for a moment, which is not so trivial to prove directly from the definition. But as we shall see, will become more approachable from another perspective. What is the kinetic distance? Well, it expresses the idea that I just mentioned. First of all, I want the probability that if I start from x, and I let the system evolve under the correct dynamics for a time scales tau, which is called the lag time. And this time scale should be the typical time scales for thermalization is in local basins. It's a metaparameter that I have to infer from experience. Actually, it's a parameter that I have to infer from experience. And I end up in Z. I want to measure how different this is from the probability that I start from a different configuration. Y, I run the same amount of time and I end up in the same configuration. I take the square because I don't want negative number inside the root. So if I look at this alone, I left some room here. I encourage you to leave some room here because this is not the end of the day yet. Okay. This is doing exactly what I wanted. Because you see, take these 2 points. If I take 2 points in the same valley, say this point and this point, within a time tau, the distribution generated by this conditional probability will be locally equilibrated within this value, right? Remember how conditional probability evolved. Ultimately, all of them converge to the Boltzmann measure, right? Because we proved that for Fokker-Planck dynamics, the limit tau goes to infinity yields the Boltzmann distribution. But we also discussed that for moderate time, it locally converges to a local Gibbs distribution, right? So for a time tau chosen comparable to this local equilibration time, if I start from here, the distribution I will get will be something like this. If I start from here, it would be basically the same distribution. It might be slightly different if tau is not chosen perfectly, but it would be a small deviation. Conversely, if I start from here, it will converge to this distribution. Right? So, these distributions do not overlap, and when I evaluate the square and integrate over x, I get a finite number, because there's no cancellation. You see? So it is really based on what we are missing in the previous experiment. But now, it is almost complete definition. It is almost a complete definition, except that we would like to avoid rescale away the fact that if I wait long enough, all of them ultimately converge, everybody converges to the same boring distribution, the Boltzmann distribution. So any difference is washed away by the natural tendency of converging towards the Boltzmann distribution, right? So to get this out of the way, I divide out the Boltzmann distribution. Well, there's also mathematical convenience for doing that. Pi of x is the Boltzmann distribution, Gibbs distribution. Now, the reason pi of x is there, as far as I understand it, has little to do with this argument that I presented to you. That is, you don't want the overall Boltzmann factor. It has more to do with a property that will follow in a minute. Okay? Fantastic! We have now a metric that I could be using for clustering, right? That knows about dynamics. Yes, except that this matrix hides all the complexity of the problem inside this propagator, which I don't know. Right? So it's not straightforward to evaluate these metrics because I would need to know these probabilities. So this is a formal expression. Now, it's like when I say, okay, the Boltzmann distribution is e to the negative b u of e x, the Gibbs distribution, divided by z. Okay, so one would say the problem of sampling equilibrium is done because the Gibbs distribution is known. Well, you know, not true, because I still have to be able to use it, right? So the same happens here. This is a fantastic definition, but as long as I find a way to estimate this distance in manageable quantities, it's useless. And now, I chose this example because you really see what, if you really want to do data-driven and machine learning in a creative way, you need to combine statistical mechanics on the one hand and formal results with computational tools. Because now I will show you that the magic happens. I will show you that you can actually estimate this distance given a set of points that you can generate with your simulations. So I show you that the kinetic distance can indeed be estimated, okay, using a finite set of points, say n data points. And in doing this, the procedure that leads to estimating d will simultaneously yield the data-driven, rigorous definition of ideal slow collective variables. Not physics-based, intuitions-based collective variables, data-driven. So, I'm going to give you a hint. We're not going to the details. I will give you a hint, okay, of how, using statistical mechanics, you can write this distance in a different form, and how using some algorithms you can use this new form to compute it efficiently. And this new form that I'm going to prove you will contain also the very definition of ideal collective values. Okay? So let's go. The key is to use the spectral decomposition that we studied. So now you begin to see why we spend so much time to do math, even if we wanted to do simulations. Because with this math, we now can make sense to problems that are physical. Okay? The spectral decomposition tells me that this propagator that I'm interested in computing can be written as e to the negative lambda n tau, right of n z, left of n x. Remember, where r of n are the right eigenstates of the Fokker-Planck equation, and left eigenstates are the eigenstates of the adjoint Fokker-Planck operator, or left eigenstates of the Fokker-Planck operator. Okay? Remember this? I also want to remind you that the following orthogonality relationship applies. Because remember, the Fokker-Planck operator is not Hermitian, so it does not have just one set of eigenstates, it has both left and right. So if I write the left and right in terms of those of the Hermitian version, this is the orthogonality condition. But once I translate that into the non-Hermitian eigenstates left and right, this is the orthogonality condition. Okay? Okay, so basically what you want to do is to put this in this and turn the handle. Okay? Wow. How much do I want to go? Yeah, fine. I promised you that I was not going into too much math, so let me not go into too much math. It turns out that if you put the propagator there and you use this orthogonality relationship, so first of all, you have two summations, one for this and one for this, right? And when you take the square, you have cross terms. However, you also have an integral of z, right? So if you use this, some terms will cancel because of orthogonality, and other will simplify. Now, I want to make sure that I have given the correct definition, so just give me a second. I don't want to have misremembered on top of my finger the definition that yields the results. So let me just very quickly check on my notes. Oh, this is not it. Recently I sent an updated version of the notes. Okay, here we go. Come on. Zagemach loop. Entropy stuff, stochastic dynamics, Radgerd, energy landscapes. Okay. Yeah, there we go. No, it was right. Okay, so dxy Ah, sorry, of course there was a mistake. If there is a root, there is not a square. Right? So D was this, that D squared is the one without the root. Right? Now I keep D with a root. Well, it turns out, after using this, that this simplifies significantly. There's only one sign, which makes sense because anytime I have an integral with left and right here squared, things simplify very nicely. You got delta functions, Kroneker's delta. So you got one sum. You got -2 lambda n tau left of n of x minus left of n of y squared. The integral has disappeared because the integral disappears when you do left of n of z, right of n of z equals delta m of n, right? That's why you don't get the integral here. And that's why you won't get the second sum here, because this kills it, okay? Now, let's define psi of n of x as e to the negative lambda of n tau times left of n of x. So basically, you're rescaling the left eigenstates, you see, with an exponent of the corresponding expression. But before you do that, perhaps it's better that we stay on this. This is an infinite sum in principle, right? Because the dimensionality, the number of eigenstates of a continuous operator is infinite, right? However, all the states with large eigenvalues, much larger, with relaxation frequencies larger than 1 over tau, don't contribute, right? So if the system has an intrinsic metastability, we have already discussed that the spectrum of relaxation frequencies will contain a gap, right? Remember this? With slow relaxation frequencies corresponding to the number of basins and arbitrarily many large relaxation frequencies. Okay? Now, if there is a gap and tau, so this is the gap, these are the fast, and tau is chosen here, tau to the -1, right? So the time scale is in line with the slow relaxation process, is longer than the fast relaxation processes, okay? All the eigenstates above the gap are exponentially suppressed, right? I repeat, if I have a gap in the spectrum, I have fast relaxation processes and slow relaxation processes, right? And if I choose tau to be longer than the fast relaxation processes, meaning I choose tau sufficiently large for a system to equilibrate locally, right? Then all these processes, all these contributions that are infinite, are exponentially suppressed, because this becomes much larger than 1, and e to the negative infinity is 0. Which means that I only have to retain a summation to exponential accuracy between the first m eigenvalues below the gap. Well, the first, remember, L0 is constant. You're not really interested, so let's go from 1 to m minus 1 or to m, whatever. First m eigenvalues below the gap. Okay? So I don't really need infinitely many eigenstates. I only need m. Okay? I didn't tell you how to evaluate the states or these eigenfrequencies. And that's where the magic happens. But suppose I was able to get the states and to get these frequencies. All I'm telling you that if I were able to evaluate these L's and these lambdas, I would need only m of them, right? Now I do what I promised to do. I incorporate this factor within, I multiply this by this. So I bring it in. So if I do this, the diffusion, the kinetic distance between 2 points is the Euclidean distance in these embeddings, in this new space. Sorry, psi. Whew! You see, if you bring this inside, okay? Sorry, let me write it. I write it in a new. I write it here, in fact. The key result is this. From 1 to n. Right? If you believe in this, which you have to because I didn't tell you to prove it, all you need to do is to bring this inside the square and use this definition. We give you this.
So the constraint is that I choose
Tau is sufficiently long to be faster than the fast relaxation processes. Okay? But now you see, suppose I'm able to evaluate L of n of x for a moment, which is not a trivial problem, but that's where the magic comes. Okay? Suppose I'm able to compute L of m then, and the corresponding eigenvalues. Then, something that is intrinsically non-geometric, namely the kinetic distance, is mapped by the x going to psi n of x, right? Into a finite dimensional space, m-dimensional space, typically small, maximum 10, and it's an Euclidean distance in this space. What does that mean? If I have a point, x, so what does that mean? Now, this is what we really want you to understand, and it's the beauty of this, the elegance of this. Let's consider our C-shaped problem we did before. And let's take 2 points, x1 and x2. Okay? Now, x1 and x2 are close along the x direction. So if I only have one collective variable and I use the x direction, I would say they're close points, but they're not. Okay? And indeed, the kinetic distance will tell me they're not. Okay? Because if I relax this, here is a state, here is another, and the two distribution will not overlap. Okay? Now I build an embedding, meaning a map between the point in the two-dimensional space and the point in this space of n. Okay? There are only, here, say this is quasi-two-dimensional. Likely there are only 2 relevant coordinates because everything else is not relevant. So, if I map these 2 points on the plane psi1, psi2, okay, I will get 2 points. One is the point psi1 of x1, psi2 of x1, okay? And the other one is psi1 of x2 and psi2 of x2. Well, these 2 points, will they be close or will they be far? Far! Because in this space, the Euclidean distance measures the kinetic distance. Now, if I go back and I take the problem that I said before, but now I do it in a two-dimensional space, like I have a large basin, a transition state, and a small basin. A point here, x1, and a point 2 here, will be mapped to 2 points, and they will be distant. However, these 2 points will be mapped into this plane to close or distant points. These 2 points. Close points. You see, what this mapping does, it compresses points that are kinetically close to geometrically close points in this embedding. And spread out points. For instance, these 2 points here are very close geometrically, but they will be distant in this plane. Okay? Wow! Fantastic, right? Ideally, this is doing exactly what I need. Except that I need to. And by the way, it also tells me how many slow coordinates I need. Right? Because this Euclidean space is n-dimensional. Right? The number of eigenstates below the gap. Right? So, if I can get the eigenstates and the eigenvalues and the left eigenstates, okay? If by miracle I can estimate the left, I can associate to each point the value of the corresponding eigenvalues, the value of the corresponding left eigenstate at that point. So I can do these embeddings. Then I've solved all the problems. I know that these psi coordinates would be my ideal collective variables. I know how many there are. It looks, however, an impossible task. Because what I'm asking you is basically to solve the Fokker-Planck equation. To diagonalize the Fokker-Planck operator in whatever meaning. It looks like an impossible task. Right? But if you think about it, I'm asking for much less than you would imagine. I'm not telling you to compute the function L of n of x so that you give me x, whatever it is, and I give you the value of L. All I need to do is I have a set of points, x1, xn, that are generated by nd, and all I need to do my analysis is the values of these eigenvalues at those points. I don't need the values of these eigenvalues in somewhere in between these points. Okay? So I only need the value of this and the discrete points that I have in my ensemble. Correct? So it is not as hard as solving the bloody Fokker-Planck equation. It is getting the values of the eigenfunction, the left eigenfunction of the Fokker-Planck in a discrete set of points. Still seems a formidable challenge, but it's much less impossible. Okay? You with me? Now, the magic and what I really love of this is that mathematicians sometimes pull out the magic out of the hat. Kaufman and Lafont were able to give you a very, very beautiful, elegant, and computationally surprisingly efficient way to solve precisely this problem. Given so, Kaufman and Lafont define what is now called as the diffusion map formalism. What is the diffusion map? Is the following problem. You have a set of points x1, xn that are drawn from some equilibrium distribution pi of x. And we know pi of x is in fact the Gibbs distribution. Okay? So I must have been able to generate and sample the Boltzmann distribution. Okay? So this is not an approach as it is now for sampling. It is an approach for given sampling has been solved, interpreting. I'm about to publish a paper to turn into a sampling algorithm, but this is not yet public. So this, in the literature, this doesn't exist in other words, okay? So in the traditional, conventional way of doing diffusion map formalism, it is an interpretation. It's a way of getting the collective variables, not a way of getting efficient way of sampling the Boltzmann distribution. So we shall assume that this problem was sufficiently simple for my molecular dynamics, Monte Carlo, whatever it was, to draw configurations from the Gibbs distribution. Now, the diffusion map formalism, DM, will give me the lowest n eigenvalues where n is equal to the number of points. Okay? Will give me an estimate of the lowest n eigenvalues. Okay? And the corresponding values of the left eigenstates for each eigenvalue at each point. Okay? So exactly what we need, in other words. Let me repeat. I get n points, I draw them here in slots, which I sampled from molecular dynamics. And using these endpoints in some limit that I will have to specify in a moment, I will get n real numbers from 0 up, and I interpret these numbers as the lowest n eigenvalues. And I get n functions for each point, which is the value of L1 of this point, the value of L2 of this point, up to the value of Ln in this point. So this is in fact the square matrix. Right? This will be accurate always? No, of course not. It will be accurate if the sampling is sufficiently dense. So in the thermodynamical limit in which I have large number of samples so that each point is really close to another one. Not to another one, but to a bunch of ones. So I must have been able to populate configuration space without leaving big holes. Because of course math does nothing about what happens within the holes, right? From here to here, there's nothing here. So if I have only these points, hic sunt leones, like the Roman would say. But if my samples is like that each point is reasonably connected to others, and there are denser regions and lower regions, so I've done an exhaustive sampling of my region, I've done a good sampling, okay? The diffusion map formalism will give me this accurately. Now what happens that if this was done accurately out of this large number of endpoints, some of these eigenvalues will be incredibly large compared to the first, right? Because remember, there's a gap in the spectrum. And the number n, I decide, it's the number of points. So if there are 5 low eigenvalues, and I have 100,000 points, there would be 100,000 minus 5 fast eigenvalues, right? So I can truncate this to the lowest m. So, in fact, all these algorithms don't give you all the eigenvalues. They give you one after the other until you see a gap, and then you stop, because computing the eigenvalues starting from the ground state is so much faster than diagonalizing and getting all the eigenvalues. Okay. So by doing this, you can now truncate this into a rectangular matrix, because you have, at this point, you have n points, but only m eigenvalues, L1, L2, Lm, right? So I've managed to construct a rigorous mapping into a lower dimensional space with a dimension that is not too small to lose relevant information, yet not redundantly large to have double counting of information and to be lost in the course of dimensionality. Okay? Now, how does the first time? So first of all, before I comment on the math, let me comment on the practicality of this. This is fantastic, because if I'm able to generate good samples of molecular simulations, I might have a criterion to say how many dimensions I need. Likely, the number of dimensions that I will need will be still quite large. Okay, but at least have a criterion to start looking at the most important and worry about the still important but relatively less important later by organizing in terms of the eigenvalues. Okay? So all of a sudden, out of chaos is order. Out of an impossible problem, I know how to at least find a way through it. In the ideal world, I have a perfect sampling, I have a perfect gap, the number of dimensions of the eigenvalues below the gap is sufficiently small not to be doomed, and I get complete understanding of the molecular problem. The real world is hardly the ideal world. So typically my sampling will not be perfect. So the points might not be so dense that each point has a large connectivity to many others, which is the limit in which this works. Okay? And the gap may not be so dramatic, so I don't really know where to stop. And even if I choose to stop where a gap appears, there might be 20 eigenvalues below the gap. No, really, 10. That's my upper bound, right? which is probably too much. But at least I can start and I have ways to devise algorithms to say, okay, I do a dimensional projection to 2 or 3. But I'm not picking this out of physical intuition. I'm picking the most important thing. I might miss information, but I know that as if I keep this order, the information that I'm missing is constructively subleading in some parameter scale. Okay? So for instance, if you look at, if you draw, say you take an intrinsically disordered protein, or an RNA, and suppose you're good enough to do good sampling, which you're not. So let's say you do it in a coarse-grained model, for instance, simplified models where your beads are amino acids rather than atoms. Or we will discuss a little bit coarse-grained models later on in this course, one of the last lectures. Say your protein has a fairly broad unstructured state and 2 distinct semi-structured states. Okay? Say on the, suppose I can, the leading 2-dimensional coordinates are sufficient to give this information. How do I know? If all the other diffusion map coordinates are highly correlated to this, then I don't need them, okay? Well, I will find a fairly broad region here corresponding to the denatured state. I could be here, could be here, could be here. I have no physical intuition of where they are. And it's going to be relatively close, but not too close, because you see, to diffuse between 2 completely disordered polymer configurations may take some time. You need to thermalize into the unfolded state, right? So, but say the other 2 states maybe are semi-structured, and they will be much closer. And then you start seeing something like bundles connecting them of configurations. Because that's how in your simulation you went from one to the other. All of a sudden, a problem that was horribly complicated starts to make sense. You go from here to here, from here to here, to here. And you can structurally characterize these configurations based on a metric, a Euclidean metric, which now embodies the dynamics. Okay? Now I want to close this lecture by saying, how can it possibly be? In other words, how can, it seems, when I first read, at least, maybe it's me, but when I first read about diffusion maps, I said, okay, this is too good to be true. How can a discrete set of points carry so much information? How does diffusion map know what is how to solve a differential equation? And I will not, so let me first tell you, when you do, I will just use an analogy first, and then I will use some physics later. The analogy is, first of all, Maxwell's equations. You're all familiar with the Maxwell equations that have 2 versions, a differential form and an integral form, right? Similarly, the Schrödinger equation can be written as an equation for the wave function, in which case is operator, function, operator, function. Now I'm neglecting IH bar and k, right? Or you can write it as psi at time t x is dy propagator psi, right? It's the same equation. This is the solution of this if you want, but it's the same physics, right? But now this propagator is non-local, it has 2 points. This is a semi-local operator, semi-local meaning it contains derivatives, right? So if I discretize this becomes a matrix vector, okay? So basically, the diffusion map builds a representation of this operator for Fokker-Planck called the transition operator using the discrete set of discrete set of states. So you get a stochastic estimate of this operator. And then diagonalizing that, you get whatever you need. Okay, that's the overall idea. But how can you get? So whatever I'm telling you here hand-wavingly is not something I'm asking in the exam. Whatever I show on the board explicitly, I'm asking in the exam. So this is just for those who are interested to understand how the hell this machinery works, for intellectual curiosity, if you want. So clearly, if I have an infinite set of points that cover all space, there you go, you get a better and better representation of the propagator. That's intuitive, right? But all I have is a set of points. How do I know? How do they know the underlying kinetics? And the reason is very simple. See, if I write the Fokker-Planck equation, let me write to you the Fokker-Planck operator. Fokker-Planck operator is d squared plus b grad u grad plus beta Laplacian of u. Okay? Now, all the information about all the spectrum is contained in this operator. You right? But I also know that u is negative kt log the Gibbs distribution, right? So I could rewrite the Fokker-Planck equation where the operator is written in terms of its eigenstate. Right? Lowest eigenstate. Why? Because basically what this is telling you that all the information about all the kinetics of the system is entirely contained in the diffusion coefficient and in the potential, but also that all the kinetics of the system is contained in the overall time scale, which I can renormalize out, and in the equilibrium distribution. Because the equilibrium is mapped into the potential. So if I know the equilibrium distribution, I know everything about the kinetics. It's kind of counterintuitive if you think about it. But all the information about the dynamics is entirely encoded in the equilibrium distribution. Why? Because the equilibrium distribution is directly related to the potential, and of course, if I have the potential, I have all the kinetics. Okay? So, the diffusion map formalism works because your points are not placed at random, completely at random. They are sampled from the equilibrium distribution. And basically, the diffusion map formalism can decode the information of the underlying equilibrium distribution from the relative distance of the points, and infer, stochastically estimate the underlying distribution. And therefore, if you can solve this equation, you get all the kinetics. I didn't give you a proof. This is very, very far from being any proof of anything. But it's a justification of where does the magic hide. Now, the formalism of diffusion map is not so difficult. You can read it in the notes. But it's probably not, for this audience, justified to spend an hour deriving this. I'd rather do some more AI and machine learning applications, okay? But I find it one of the most fantastic incarnation of modern mathematics because it embodies differential geometry, stochastic process on the mathematical side, and computer science, because in the end, you have a constructive way of tackling an potentially unbearable problem. So in this lecture, we cover the problem of what is the number of dimensionality of the intrinsic manifold. How do I know more or less how many collective variables do I need? What are the ideal collective variables? And given that I can do the sampling in an efficient way, how do I compute my points project? What is the ideal dimensional projection? It's a lot of results for a single lecture. So what is left to be doing? The next lecture will be about a very similar and closely related topic, which is the concept of reaction coordinate. And once again, what is the ideal reaction coordinate? And guess what? Machine learning schemes are being used to get this concept of reaction coordinate. And then we will move forward towards machine learning applications to coarse-graining, meaning to building mathematically simplified representation of macromolecules that can be easily solved on a computer. And then I guess we'll be done, or you will be done, and you'll let me alone at some point. Okay? Thank you. Have a nice break.